In previous videos, we looked at dislocations in FCC, BCC, and HCP crystals. In this video, we'll look at dislocations in other crystals. The first example is the diamond cubic structure. Diamond cubic crystals can also be viewed as FCC, but at each lattice site there are two atoms instead of one atom. For example, for one pair of atoms at one lattice site can be 000 and quarter, quarter, and quarter. Since diamond cubic has the FCC lattice, the 111 planes are still the most packed planes, but the stacking is slightly different. Since you have two atoms per lattice site, the stacking, instead of ABC, ABC stacking, it is AA, BB, CC stacking. Let's view the diamond cubic crystal in the same way as how we view the FCC crystals, with 011 bar direction pointing out of the page and the 111 direction pointing up. And look at the projection. I used three different colors to label the AA, BB, CC stacking. Within the AA, BB, or CC layer, the two atoms lay directly on top of each other. If shear happens between each band, then this is dislocation glide. The dislocation will have half 110 Burgers vector gliding on the 111 planes, the same as FCC crystal. In diamond cubic crystals such as diamond and silicon, dislocations usually lie at 0 degree or 60 degrees to the Burgers vector. If shear happened within the colored band, then this process is called shuffle. For stacking faults, instead of taking or inserting only one atomic layer, like in the FCC crystals, here you need to remove or insert those bands consisting of pairs of atoms. So far, we have only looked at crystals having only one type of elements. What happens to dislocations in the crystals composing of two different elements? And the example we'll be looking at is the intermetallics. Intermetallics are compounds made of two elements, but these two elements occupy specific lattice points. For intermetallics, the most common crystal structures are B2 and L12. For B2, it is very similar to BCC, having one element occupying the center and the other element occupying the corners. For L12, it's very similar to FCC, one element occupying the faces and the other element occupying the corners. We will use L12 superlattice as an example. Since the L12 structure is very similar to FCC, one may expect the 111 plane is the slip plane. However, what people have observed is the 100 plane is the most common slip plane. The unit slip vector is the same as the Burgers vector in FCC, which is half 110. But if you shear the crystal by half 110, you will see something really interesting. Before shearing, you have the blue, red, two elements alternating. But at where shear has happened, you broke such order. Now you have red, blue at the interface. Such interface is called the antiphase boundary. Let's take a step further. If we keep shearing that by another half 110, what is going to happen? You will restore the blue, red ordering and remove the antiphase boundary. So 2 times of the half 110 gives you the 110, and this is called a super dislocation in intermetallics. There is a fun fact of nickel-3 aluminum which has the L12 structure. For most materials at higher temperature, the critical resolve shear stress is either not affected, like in FCC crystals, or will decrease, like in BCC metals. For nickel-3 aluminum, the CRSS could actually increase at high temperature. This is called the yield stress anomaly. If you are interested in understanding why, you can read more into the topic of Keir-Wilstoff lock. The last example we are going to look at is the ionic solids. Ionic solids are similar to intermetallics that the cations and anions, they occupy specific lattice site, but it introduces one more dimension of complexity, charges. We'll focus on the sodium chloride structure, which has FCC crystal structure. For the sodium chloride structure, the Burgers vector is still half 110, but the slip plane usually happens along the 110 or 100 planes. At higher stress levels, slip can also happen on 111 planes and 112 planes. Due to the charge balance in the sodium chloride structures, the edge dislocation is no longer the insertion of one extra half plane. You need to have two extra half planes. Let's assume we have only one extra half plane by removing the red color plane in the example on the left. The negatively charged plane, labeled in blue, will be in direct contact with another negatively charged plane, which will repel each other. The same principle applies to the example on the right. In this module, I hope you have gained a good understanding of dislocations in different types of crystals. Starting from next video, we'll move into a new module discussing how dislocations move and multiply in crystals.